All right. Any follow-up questions from the midterm? So I do have office hours tomorrow, 7 o'clock to 9:30, so if you want to talk about midterm, you can catch me then. You can probably catch me for a few minutes at 11:50 after class today, or elsewhere. I posted an announcement, but I forgot what date I said. November 13th. Okay, so there's no class November 13th. And I think that's my last unplanned absence, so should be business as usual after that. But nothing in particular going on that day anyway, so shouldn't be a big issue. All right, let's start with the previous ODP. So, well, the one before the previous, ODP 416, we were removing x's from an input string, right? And we already looked at this code, so we loop through all the characters, and if the character is not an x, then we copy it to the output, okay? And increment the output location accordingly. So 417, the one that you did Friday, the goal was to remove the first x from a string. So let's remove 1. And it's almost exactly the same code, except that it uses a flag. So there's this flag which I call done, which I initialize to 0. And done basically says, are we done removing x's? Okay, so how do you remove the first x? Well, you look at a character, and if it's an x, don't copy it to the output, unless you've already done that once. If you've already done that once, you remove the first x, now just copy the input to the output. So done means we're done removing x's. So initialize it to 0, which is false. And it's the same for loop. And then instead of just if the character is not an x, copy it to the output. If it's not an x, or if we're done, if we've set the done flag, then go ahead and copy from the input to the output and bump up the output location. And then there's one extra line of code which says if the character is an x, set the done flag to 1. And there's a few shorthands in here that you might not want to do if you're figuring this out, but they work fine. One is, I'm using done as a true-false value, and remember 0 is false, non-zero is true in C. So if I wanted to be clear about this, I could say if done equals 1, or the rest of that statement, but I can just plug in done, and if done's 1, this will be true. If it's 0, it'll be false. The second thing is, every time I encounter an x, I set done to be true. Well, that's redundant, but it's harmless. My real goal is the first time I encounter an x, after I've made this conditional check and I decided not to copy it, I want to make sure I set done to true. But I just set it to true anytime I hit an x, right? Now, I could have done an extra statement if done equals 0 and my character is an x, set done equal to 1. But I just set it to 1 every time I find an x. It doesn't do any harm. If it's already 1, it's basically a no-op. And the third thing was my for loop. I actually go up to where the input location is less than or equal to the string length instead of just the usual less than. Why do I do that? Normally you go I equals 0, I less than string length. Here I do less than or equal. What's the difference?
copy over the null terminator?
That's exactly why. Because if I go up to string length of in brackets string length in is the character after the last actual character of the string, that's the null terminator. And since the null terminator is not equal to an x, this loop will copy that null terminator to the output, and it'll copy it into the right location, which is whereveroloc is, output location. So that throws the null terminator on the end kind of for free. And if you don't do those things, you have to write more code, but the more code that you write is going to be more clear to read usually. But I shortcutted in here a fair amount. But that's not better or worse. So the real lesson of ODP 417 is this idea of a flag, right? And we use flags all the time. Flags are really powerful. They're good to have in your arsenal. Sometimes you can't get away without them. And a flag is just something you set to indicate that something's happened when you're not ready to use that information yet. You're going to want to use that information later. So somewhere later in your code, you want to know that something happened in the past. That's what a flag is for. In this case, later in my code, I want to know that I've already removed one x, so that when I come down here and I say, let's copy from the input to the output, I know that I should ignore the check for whether it's an x or not. So that's a flag, and we use them all the time. All right, so I'll start back with ODPs next week because we'll be doing C programming for program 4, and we'll be doing a lot of string processing. And so I've got some more ODPs that'll help with that. But string processing along the lines of what we've already done last week in the ODPs. All right, and tomorrow, even though it's Thursday, I'll talk about the 4th programming assignment. And we'll go through that because there's no class Friday. So we'll go through PA4 on Thursday, but PA3 still isn't due till Friday morning. So that's the usual due date. All right, let's keep talking about GDB. So we had an ODP where we're writing a calculate function that takes a string, and your string should be something like 2 * 3, and it should return 6. And so here's a calculate function. Here's some test code for it. I set I equal to calculate 2 times 3, and then I print out the value of I, and it should print out a 6. And let me just break this up for clarity. So that should print a 6. So go ahead and run this, and it prints out a 0 instead of a 6. And that's a bug somewhere, right? And this is a bug that maybe you can see what it is, or maybe you can't, right? It's a bug that late at night is usually pretty hard to spot. So let's play with GDB and see what we can do with this. So gcc-g says I want to use GDB -o calc.c, and now I can say GDB calc. Okay, so reading symbols from calc done. That's good. We've got GDB linked in. We say start to begin debugging, and now it prompts GDB in parentheses. It says it's waiting for me to tell it what to do. All right, so let's make a list. gcc-g, and so on. That's how we compile. GDB program. So this is compile. This is how we run inside the debugger. And then everything else here is inside GDB. So we say start, which is just starting the debug process. And it'll show us the first line of code that it's about to execute. Okay, I can do a few things. I can say continue, and it'll just go ahead and run the program. And it says continuing, and it prints out the result I equals 0. So if we want the program to just run normally, we can say continue. And remember, you only have to type enough letters to make it unambiguous. So CONT works fine for continue. And it showed us I equals 0 instead of 6, so that's a problem. So let's say start again. So if I want to run one instruction at a time, I have two options. I can say next or I can say step. Okay, the difference is if I say next, this will basically execute line 9 and it'll take me down to line 10. Line 9 is where it calls my calc function and it does all the stuff in there, and all of that happens before GDB comes back. And when it comes back, I'm sitting here at line 10. So I missed all the action that was happening inside calc. And I can print the value of I, right, and see that I've got a problem. But I didn't see what actually happened in calc. So next is what we call a step over. It means execute one line of C code, but if that line happens to be a function call, execute the whole function call, right, before you come back to the prompt. So if there's a function call, it does the whole thing. And for example, it's about to execute this call to printf. If I say next, it'll execute that whole call. It does what the printf function does, and now it comes back to line 11 of our function. Okay, so let's start again. And if you decide to start before it thinks it's finished, it'll say the program's still running. Do you want to start from the beginning? You can say yes. Okay, so instead of saying next, I'm going to say step. And step is a step into. Which means execute the next line of C code, but if this line is a function call, just execute the call to the function and stop inside the function. So it steps into the function instead of going over it. So here if I say step, now we're sitting at line 14. That's the first line of the calc function. So now we can actually debug the code inside calc. And it shows you what argument was passed to the function. In this case, it was an argument called buffer. So let's list. Right, so our function is called integer calc, and it takes an argument called buffer. And it shows us that calc was called with an argument of buffer. This is the value of buffer. And it knows it's a car pointer, so it's showing us the value of that, which is 2 star 3. But I could print buffer, right, and it shows us the hex value of that. All right, so, and it said we were at line 14, so we're about to start executing this calc function. So let's say next. And it's about to call scanf, and it's going to pass buffer. It's going to parse it into these three pieces. It's going to store the values in n1, op, and n2, and it's going to set stat equal to the return value. Okay, I'm going to say next because I don't want to go into my scanf function. I don't want to debug that. That's system code. I want to just execute it and come back to line 20. So it calls scanf, it returns. So now I can do things like print stat. Stat was 3, that's good. I can print n1, that's 2. I can print n2, that's 3. And I can print op, that's a star. So scanf did exactly what we expected. It took 2 star 3, it broke it into the number 2, the operator star, and the number 3. And stat came back with a 3. My code doesn't check stat, but there was no error here anyway. Okay, so the first thing says if op equals plus, result equals n1 plus n2. Well, let's check the value of result first. And result is 32767. It hasn't been initialized, so that's fine. Okay, it's going to see if the op's equal to plus, and if it is, it's going to set result to n1 plus n2. Checks to see if it's minus, checks to see if it's a times, and it should be a times, and we print result, and result is 6. So our code's working great now. All right. And then it's going to check to see if it's a slash, and then it's going to return result. And it comes back to our main program, which said I equals, calc. When we return 6, we print out I is 0. So something weird is going on. Okay, so I want to look at the behavior of this calc function a little more closely because something is weird. So I'm just going to say start, and I'll start from the beginning, and we can say step, and let's go through next. Alright, so it did the multiplication. We look at result, result is 6. We execute this next if statement. It's about to return result. Let's double check result, and guess what? It's equal to 0. So we've pinned down our bug. We know that somewhere between 23 and 25, result changed from a 6 to a 0. Right? It was fine at the end of 23. We looked at the result and it was equal to 6. We executed line 24 and result changed to a 0. Well, the only way that would happen was if op was equal to a slash, and we know op's equal to a star, right? This is your suspension of belief. Something is wrong. You got to be open to the possibility that the world is different from how we think. So let's print the value of our operator. It's a slash. Alright, let's do this once more. Let's start over from the top. Let's step into here. Let's do our scan, print our operator. Our operator is a star. Let's go again. Let's make sure the operator is still a star. It's suddenly a plus. Let's step once more. Let's print the operator. It's suddenly a minus sign. And at this point, you probably get an aha, right? OP is changing. Why is OP changing? Because I got a single equals, right? The most annoying bug in all of C. Okay? And you can stare at this for hours as just code and you're not going to see that, right? Because your brain is saying if x equals, if operator equals plus. You're seeing a conditional, not an assignment, right? But the compiler saw an assignment. So using GDB sometimes can sort of force you out of your convictions that things are a certain way, and it kind of forces you to see something different is going on. And that can help. In this case, I've got a single equal instead of a double. So that's one way that GDB can help us. And it's really about sort of trying to, we know there's a bug in calc because we call calc and we print out the result and it's wrong. But it's trying to narrow down exactly where things are going wrong. And just to wrap it up, what happens here, while our operator is a star, when we execute this if statement, the operator changes to a slash because it was assigned to be a slash. And so this says if parentheses slash, and slash is not 0, so it's true. So it's setting result equal to n1 over n2. n1 is a 2, n2 is a 3. 2 divided by 3 is integers is 0. So it's doing exactly what it was told to do. It's just not what we thought we told it to do. Alright, so we quit out of that and you change your code to double equals and you run it and it should work fine. And if you didn't have GDB, right, you could go through and you could throw a bunch of print statements in here, but unless you know what you're looking for, you're not sure what to print. Now you could print everything, and you could print the value of n1, n2, op result, and stat, each line of your code. and get a bunch of output and eventually see what's going on. But that's not always a practical way to do it. You can be a little more tactical in finding what you want to look at with GDB. All right, so here's a previous ODP where we were trying to remove x's from a string. And so test code, we take he x low and we remove the x and we print it out, and it should just be HELO. And we've got a variable looping through our string, that's k. We've got an output variable a, and if the character in the input's not an x, we copy it to the output. We throw a null terminator on the end. And if we run this, it seems to work fine. So you do this and you're not assessing successfully. So when I talk about pretending you're a computer, writing down your variables and going through the code line by line, one of the things I mentioned in that posting was don't assume anything about the initial values of variables that you haven't declared. So k equals 0, because I say integer k equals 0, so I know k is equal to 0. But character temp 120, I don't know what the value of that array is initially. So my suggestion was just pretend that your array is filled with a bunch of question marks. So I'm going to do that here by using the string copy function as part of string.h to copy a bunch of question marks into temp, just to give it some value that clearly indicates I don't know what it contains to begin with. And if I do that and I run this, I'll see this extra character stuck on the end. And that extra character is actually a question mark, which is what I initialized to. So something's going wrong in my code here. So let's debug this. So we're going to say start, and I'm going to jump over the string. Well, let's see what temp is first. Before we do this, what is temp? Well, it's 24 nulls, followed by GENU, followed by some more nulls, a tab, more nulls, a back quote, and a V, and then some other stuff. And remember, I warned you, setting up the null terminator is a tricky piece of this ODP. Well, I've got 24 null terminators sitting in the beginning of my array. If I never set up the null terminator at all, this code's still going to work if my input string is smaller than 23 or 24 characters, because I've already got null terminators sitting in temp. When I say string copy a bunch of question marks into temp, I don't have that set up anymore. My first several characters of temp are now question marks followed by 14 null terminators, right? And that's why I'm seeing an error when I run it with this string copy first, because I'm apparently not putting the null terminator in the right spot. So let's step into our rem function and let's start looping through. So it's checking element 0 of in. In is our input string. And it's checking to see if element 0 is different from an x, which it is. So it should copy that to my output string. And if I print the value of a, it's originally 0. Copy that into the output string, now a is equal to 1. And if I print my output, it's got my h in the beginning. Okay, so I copy the first character. We go back up to the top of the loop. If input character 2, array element 1, is not an x, it should copy that into the output. And now if I print the output, it's got the h and the e. Looks good so far. Now k is equal to 2, so we're looking at the third element. If I print in bracket k, that's an x. So we don't want to copy that. So it says if that character is different from x, and it skips the assignment. And it jumps back up to the top of the for loop. That's good. Okay, k should be incremented to 3. That should be the letter L. That's different from x, so it copies that to the output. And we can double check. A is equal to 2. Our output is H followed by E. If we write into character 2, that's going to come right after the E. So go ahead and execute that assignment, and now look at your output. And it's an H, an E, and an L. So we're in great shape so far. Increment k once more. K is equal to 4. And that's the letter O. And that should go into the output string. And so HELO. Okay, we're looping up to string length of in. I can print string length of in inside GDB, and it tells me that's equal to, that's not useful. Alright, we can't print the string length of in. Never mind.
Cast it to an integer, maybe?
That's a good idea. But that's not going to help us. Okay, forget that. Can't print the string length of in. But we can print in, and it's HEXLO. Okay, which has a length of 5. And k is equal to 4. So if we increment k, it's not going to be less than the string length of in anymore. So let's go once more, and we kicked out of our loop. Alright, so our rem function said for k equals 0, k less than that. If that, set the output equal to that. And now we're down at line 20, we're outside of our loop. And it says increment a. Okay, let's see what the value of a is right now. It's 4. So if we say next, it should increment a to a 5. And now it's going to write character 5 of our output to be the null terminator. Well, let's take a look at out. It's HELO question mark. And where is character 5? Character out bracket 5. All right, we start from 0, so H is the 0, E is 1, L is 2, O is 3, question mark is 4. Element bracket 5 is this second question mark. And if we zero that out and we print out, we've got that question mark on the end because we put the null terminator one spot too far over. Where did we want the null terminator to go? We wanted our output to be HELO question mark. So character 0, 1, 2, 3, we wanted element 4 to get the null terminator. Well, that was the value of A until we did this A++. And then when we did that, we basically moved the null terminator one spot too far over. So the whole trick is if we hadn't have done this, the null terminator would have gone at the end of the HELO, and we would have had success. So that's hard to fix in the debugger, but we can try this. So fix that, recompile it, run it, and there's the correct output. So it's using GDB to watch what's happening and compare it to what you think should be happening, and hoping that you find a discrepancy somewhere. And that tells you where the issue is. And this can, yes?
So when you use GDB to print a string, like out, you print out, you will print the address first and then the content of the string. But when you print temp, I didn't understand what does it print. Yeah.
I believe that's because I set it up as an array instead of a car pointer. And they're the same thing internally, but to GDB, I'm not thinking of this as a pointer, I'm just thinking of it as a string. And so it's just showing me the contents of the string. So let me try this. If I'm not totally making this up, then this should print out the address of temp and then the value of it. Right? Because when I wrote the code, I said temp is a car star, and GDB knows that. And so when I asked for the value of temp, it says, oh, this was supposed to be an address. This was a pointer. I'm going to show you what it's pointing at. Right? And then I'm going to show you what's stored there, which is 14 question marks. So it's a feature slash bug, depending on how you look at it. And this is an interesting one. Because if I let this program run, I actually get a seg fault. And I get a seg fault at line 19. Right, so if I just run this directly, rem 1, it just says seg fault. So you can seg fault inside GDB. So I'll start and I'll say continue. But it'll tell me where it was when it got the seg fault. It was at line 19. It was saying out a++ equals nk. Well, I can print k at 0. I can print in. It's our input string. I can print in bracket 0, and that's just the letter h. Nothing wrong there. I can print a. That's a 1. I can print the value of out. That's just that. I can print out bracket 1, and that's just a question mark. So I can read from the address on the left, I can read from the address on the right. It must be I cannot write to the address on the left. So I can cheat and do an assignment inside a print statement. I can say print out bracket 1 equals h. Oh, that shouldn't have worked. I'm cheating on something. Okay, don't do that, because we're cheating, because we're inside GDB. But something went wrong with that assignment statement, right? Sometimes things are different when you run them inside GDB. The problem here, and you just have to know this, there's no way we can actually get GDB to tell us other than something went wrong when we said out a++ equals nk. The problem here is that when we say car star temp equals string, that takes those question marks and it puts it in an area of memory that we're not allowed to change. Right? Because it's kind of like a constant to the program. So it actually puts it in an area of memory, a segment, that you can read from but you can't write. And when we try to write to it, it throws a seg fault. And that's just something weird that you need to know. So that's why I did string copy originally. And if you want to know the address of temp, we can say print ampersand temp, and it'll tell us where it's stored. And notice it said an address that starts with 7FF. That's usually writable memory. That's actually the stack, like the 270 PIC processor stack. That's usually read-write. Whereas before, the address that it was using for this thing was something that started with a bunch of 5s. right? And that's read-only memory. So you get to know a lot more about your processor and your operating system than you want sometimes when you're doing this. It's one of the reasons why, you know, I tell people in 270, even if you're just going to be a software person, you're never going to touch hardware, you still need to understand things like architecture, things like indirect addressing and so on, because it affects how the compiler writes code, it affects how the CPU runs your code, and it affects your debugging. And if I want to examine memory directly, I can say something like X for examine, and I can type in an address. Perhaps. Yeah, or I can just type it. Alright, and I can actually look at the contents of memory. So on the left is a memory address, on the right is the contents of it, and I'm looking at it 4 bytes at a time. And the next 4 bytes look the same, and the next 2 bytes look the same, and then there's a 0, 3, and a 0, 0. And this is the ASCII code for a bunch of question marks. 3F is a question mark. And so I'm looking at my question marks and then a bunch of nulls. So there should be 14 nulls, and it says repeats 14 times. That's what those zeros are. So there's 2, there's 6, there's 10, there's 14, and then 47 is the ASCII code for an uppercase G. All right, so we're seeing the actual memory of the processor right now. And if I just print temp, GDB will interpret it for me, but we can always look at it ourselves. And I can also say examine a byte at a time, if that helps. And I can say examine it as a character, X/C, and see 1 character at a time. And there's, you know, a zillion options just for examining memory. All right, so this can be a little laborious. How laborious can this be? So the worst bug I ever tracked down took me about 2 weeks of doing what we just saw for about 5 hours a day. And I did this for about 14 days, so about 60 hours of just stepping through code 1 line at a time. This next instruction says take this, and if it's equal to this, do that. Check the value of this, this, and that. Execute the instruction, now check the value of this and that, and make sure everything worked okay. I don't know how many thousands of lines of code I stepped through like that over the course of 2 weeks, but sometimes that's what it takes. And man, that was a big epiphany when I found the bug. That was a worldview changing epiphany. Usually it's not going to be 2 weeks, but I was debugging code that was not my own. It was my code that was interpreting another set of code that was millions of lines, and I had no idea what it was supposed to do, so I was just stepping through it blindly. But if it's code that you've written, you can usually, you know, have an idea what's going on, and you can do some shortcuts. So here's our Rem1 code. So I can list my code out, and I know I've got a problem somewhere inside my loop. Well, here's what I can do. I can say break 15, and I can just say run. And it'll go through everything at full speed until it gets down to line 15, and then it'll come back and ask me what I want to do, right? Or maybe I know that the for loop does its thing, but there's a problem somewhere after line 20, so I can say break 20, continue, and now it's gone through the whole while loop 5 times, exited the while loop, and now I'm sitting down here at line 20. And at this point, you know, I can start looking at, you know, what's my input, what's my output, what's the value of A, and so on. So if you understand your code, you don't have to go through one line at a time. You can skip forward and do things like that. You can also do things like, say, I want to watch the value of a variable. So anytime A changes value, I want you to let me know. And I can just say continue, and it says, oh, okay, I just changed A from a 0 to a 1. Why? Because I just did this out A++. And then I can continue, and now it just changed from a 1 to a 2. And now it changed from a 2 to a 3, and now from a 3 to a 4. And now it changed from a 4 to a 5, and it's about to say out bracket A equals null terminator. So you can set up watch points to see when variables change, and that's really useful, right? If you know that your value has a correct value at some point, but somewhere along the way something's changing it, you can put a watch point on it. And when it changes, the debugger will tell you, and it'll bring you back to the debug prompt, and you can see where you are in the code. And in this case, it's about to execute line 21, so I can say that line somewhere right before that, in this case line 20, must have been the thing that changed the value of A. So we can say print, we can say X, which is examine, we can say break, a number or a function name, we can say watch, a variable, and I could say break rem, and it'll put a breakpoint at the beginning of the function named rem. Or you can do a line number. And this is probably a sufficient set of GDB commands to do most debugging you're going to encounter, at least for here in 222. Start, continue, next or step, print or examine, break and watch. Gives you enough access. So let's go ahead and run this, and let's get down to line 20. And before I do that, A is equal to 4. When I execute this, A is equal to 5. So I can change the value of A back to 4 by saying print A equals 4, and now A is equal to 4. So now when I execute my out bracket A equals null terminator, it puts it in character 4. And now when I do my print statement, it prints out the correct string. So you can change the value of variables by using print. And generally you can do a lot with print. So I can print temp. I can say print f gets temp 100 comma standard in, and I can change temp to a bunch of A's. And how did I do that? Because I called the fgets function inside the debugger. So you can call most functions inside GDB also, which is really useful. It's a really rich environment for working in. Sometimes you mess up. Sometimes you want to execute this print statement, but you accidentally say step, and you find yourself debugging printf.c. We're at line 28 of that, but we don't have access to the source code here. So we can start stepping, and we can see what lines we're executing, and now we're suddenly inside this function called vprintf at line 1244, and this is a big quagmire, right? So if you want to get out of that, just say finish, and it will jump down to the end of that function, and then you're back to debugging. So finish kind of gets you out. The other function that's useful is mode, and if you say mode ASM, oh, it's not mode. Layout. Say layout ASM, and you get this nice graphical view of what's going on. But this lets you debug in assembly language. So we're in our main function here. You can see main plus however many bytes beyond there. But here's the assembly language corresponding to each of our statements. And I can say step, 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 and right, we're inside our rem function now. And so that's another way to look at your code if you want to get down to assembly language level, but that's a different topic altogether. All right, so last thing I'll put on here is finish, which basically says go to the end of my current function where we're about to return and then come back to GDB. All right, so my suggestion, start playing around with GDB, right? When you've got some code in C and you understand it fairly well, start running it with a debugger and looking at variable values and so on and so forth. Get comfortable with it, and then you can start using it to actually debug.